Let's see here. Let's do another one. What time is it? 10 minutes to do that. Let's talk about non-uniform. I have one other one, but it's trivial. I'll put it on the website or something. We drew in on the free body diagram, so why do we say it's 0? It wasn't 0 yet. Right? We were saying there could be a normal force there because we could go at any different kind of VT, but now you realize we're going through a mental process to realize, oh, we want the special case where n equals 0. It depends on how fast you're going, so we went ahead and wrote it. Okay. So I just want to point out then with our final 10 minutes here that there is more than just uniform circular motion. This is the second, this is the second half. Class is almost over, right? I don't know. I forgot. Okay. What if uniform, or what if the motion is not uniform or circular? What if it's just some general motion? Are any of these values useful? Right? Can we think of things rotationally? For example, let's look at the projectile. I mean, you know this one. We've thought about it a lot. We set something off and we shoot it at V naught at some angle theta. And what does it do? Ooh, like that, except it would fall underneath there. Is there anything circular about that? Right? It's parabolic. It's a parabola. But it's circular in one place. And if you have an appreciation of symmetry, that answers the question. There's only one unique place on that trajectory, and that is at the apex, right? If it's circular here, it'd have to be circular there. If it's only circular in one place, it must be circular there. Right? So you could argue that that is going through uniform circular motion there. So it's at the apex because that's where V is perpendicular to A. That was kind of one of the definitions. I may not have said it real clear, but one property of uniform circular motion as it goes around is that V is tangential, A is radial, in. They're always perpendicular to each other. So when you're here, there's V and there's G. Or there's A, right? It's acceleration due to gravity. So they aren't perpendicular. And when you're here, there's V and there's G, or A. Not perpendicular. But the special part is right at the apex, your V is completely sideways. And your A is completely down, right? AY. I'm sorry, I changed the label every time. There we go, AY. So we could say then that AC, the centripetal acceleration, basically just equals G at that point, at the apex. So who cares? Right? I forgot why we care about this. Let's see. So what you could do then is you could have a point and you could inscribe a circle in it and say, well, you know, it's kind of like circular motion at this point. Who cares? We probably won't have time to get to. But let me give you an example of, like, let's do a calculation with this. Let's do something fun here. N is, somebody asked, is N 0 when the ball falls off the track? No. N is undefined because the ball's not touching the track. So there is no N. It goes to 0 and then it doesn't exist anymore. So you can decide if not existing means 0. This isn't a philosophy class. So what we could say here, the fun question I want to drive is okay, so say you're given the standard trajectory, V naught at theta, right? So the standard situation, V naught at theta, is H or D larger. And what does that mean? By H, I mean the height. All right, the height of the trajectory, which we have a formula for. And what is D? The diameter. 2 times the radius of the circular motion happening there, even though it's not a circle. So what I want to show you is how to think about how to get that that radius. Like one problem might say, what's the radius of the motion here? It might be infinity. It might be 0. So let's look at that real quick. So H you would look up. In your notes, you could do this on the pledge problem. We know it's V naught squared sine squared theta over 2G. Right? straight from our other derivations. But how are we going to get the radius of this circle? Well, if at that moment it's uniform circular motion, then we know that, why is there a 2 there? Oh, I multiplied by a 2. Okay, yeah. We know that the sum of the forces equals MAC, right? So we know that the sum of the forces in C equals the mass times acceleration in the centripetal direction. So we say at this moment it's circular, so we say this equals mass times G, because G is a centripetal acceleration. And then, I'm sorry, no. Right. The force is mg and equals mv squared over r. That's what we have to say. There we go. That's what I'm trying to do. And then we would cancel the masses. All right. And then we would say, let's put a 2 here and a 2, or let's say a half to get a 2 down here. And then what v is that? We've got to realize, wait, that's not this v. It's this vx component. Vx component like that. Okay. Yeah. Let's get rid of this. Okay, I screwed this derivation up, so let me put this away. I put a 2 in the wrong place. So let's see if we're all together here. The centripetal force is the force that's driving into the circle is mg. We know that's equal to mv squared over r, and we know it's vx, right? So we cancel the m's. We got g, and what is vx? Fortunately, vx is constant, right? So we're combining the stuff we learned before to this. It's v naught cosine theta equals v naught squared cosine squared theta over r. So we just replace the r and the g like that. But the diameter is 2d, is 2r, right? So d is 2 v naught squared cosine squared theta over g. So we say, which one is bigger? Oh, then you would just plug in your numbers and say which one is bigger. But you can kind of tell that if you're at a low angle, if theta is small, cosine is 1 and sine is teeny. So that's going to make the circle is going to be bigger if you're like that. See, then the height is small and the circle is huge. If you have something like this, then the height is big and the circle is small if theta is big. Okay? So it kind of makes sense. So I think I put that one in there as an example of how we could combine different parts of the class, right? That'd be a good exam problem where we say, here's circular motion and a projectile, and let's combine the two numbers. So let me answer a few of these. I'll shout these out. Is n equal, oh, there's only one. Why are h and d not the same? Yes, that's the point. Why are h and d not the same? Is there different things? We're looking for different things. One was the height of the parabola, and one was the diameter of this circle. We're just trying to compare them for fun. What a disaster.